So good evening everyone. Welcome back to the NPTEL online certification course for problem solving and doubt clarification. So we are in week 7 of water and wastewater treatment, and as you all know, the course instructor is Dr. Bhanu Prakash from IIT Roorkee, and I am one of the teaching assistant. My name is Akash Saha, and I am a PMRS scholar at the Department of Civil Engineering at IIT Madras, where I am pursuing my PhD in environmental engineering. So till week 6, we looked into the aspects of wastewater treatment majorly. We saw some basics and then the different units of wastewater treatment. So from now we will start with the water treatment. So first we have looked into this water demand. What are the sources of water? How to calculate the water demand? Okay, what are the various factors? How to do population forecasting and all? And what is the variability of water demand? Okay, and then we also discussed about what are the different water quality parameters. Okay, we have seen some case studies, okay, about the surface water quality at Ganga river, at Rishikesh, and all those things. And then we discussed about various kind of parameters like turbidity, pathogens, DPBs, and some heavy metals. And then we switch to the water treatment aspect, the basic layout, what are the different unit operations for surface water treatment, what are the characteristics of the particle to be removed, and then we looked about the electric charge, the size, the EDL, that is the electrical double layer, and then particle stability. And then we dig deeper into the electrical double layer, what is meant by zeta potential, how to destabilize a colloidal particle, all those things related to coagulation and flocculation. Okay, then various type of coagulation mechanisms, starting from the adsorption and charge neutralization, sweep coagulation, and then how to do coagulation with alum, and what is the alkalinity requirement. So lot of things in this week's lecture. Okay, so we will solve some MCQs and numericals as well for this week's content. Okay, and as and when if you have any doubt, you can unmute yourself and ask it. We'll start with the first question. So it says that match list 1, that is the delta P, with the most probable option in list 2, which is the various population forecasting methods. And here delta P represents the change in population between 2 decades. Okay, so suppose 2011 to 2021, what is the change in population? It is marked with delta P. And then 2020 delta P1, then 2021 to 2031, the change in population is marked in delta P2. So based on the type of population forecasting method, okay, we have some general guidelines regarding the delta P. So if the variation is within this range or is following this particular kind of trend, we will use particular type of forecasting method. So we have the arithmetic, geometric, and the incremental increase method. So please try to answer. So in the first list, the first option is all the delta P are more or less equal. So there is an equal increase in the population, equal increase or equal decrease, whatever. Majorly equal increase only, because we are only talking about the increase methods for population forecasting. And then in the next one we have sometimes increase, sometimes decrease, so that kind of thing is there. And then in the third one we have always in increasing order, if the delta P is increasing for all of them.
Option A, sir.
Option A. So you are saying that the first one will be arithmetic increase, then incremental increase, and then geometric. Yeah, I think this is the correct answer, because in arithmetic increase, we assume that the increase is more or less same. Okay, if we have a constant kind of increase in each of the decades, we go for arithmetic increase method. Then in the incremental increase method, we find the change in the increase. Okay, so that's why it can sometimes increase or it can sometimes decrease also. So that's why we see what is the incremental increase overall in all the decades. And in the final one, in the geometrical increase methods, we see a constant rise in the increase in population. Okay, so majorly for new cities or which are being settled up very recently due to some economic or urban growth. So in those kind of cities, we do this geometrical increase method. Okay. So as you all know, in the geometrical increase method, we will get the maximum population being forecasted. Whereas in the arithmetic one, we will get the like among these three, we will get the least population forecasted, and incremental will be somehow in between them. Okay, so that's how the trend goes. So I think it is clear to all of you. We'll move to the next question. It says that select the correct option regarding the statements below. So statement 1 says ionic strength increases with the charge of coagulant. Then electronic double layer thickness decreases by increasing coagulant dose till a certain limiting concentration and increases with excessive dosages. So what do you think? Are both the statements true or wrong, or some or one of them is correct?
Not getting it, sir. Sorry.
Okay, so just imagine like, okay, I will give you some hints, then you can think about it. Just a minute. Okay, so week 7. So suppose there is a particle, okay, there is a particle over which the it is a positively charged particles. Okay, the overall charge over it is positive, and or negative, whatever it may be, or it may be positive or negative, and we are putting some kind of coagulant which is majorly negatively charged. So these charges will tend to form a layer over it, right? So now see the statement. It says that electronic double layer thickness, which is nothing but the layer of the particles that are being formed, decreases by increasing the coagulant dose. So it says that this layer which is being formed outside, it is getting some kind of compression as the as more and more coagulant dosage is being increased, but only up to a certain limit. Okay, but only up to a certain limit, above which this again the this layer will start increasing. This layer will start increasing. So is it true or false? What do you think? Because may just think that this particle is positively charged and some counter anions are getting deposited or uh, getting near the surface. So what will happen? So it will try to neutralize the charge, right? So whatever the plus sign, minus sign, it will try to neutralize the charge. So in that way, the the electronic double layer that is being formed over all the particle, okay, it will keep on getting compressed. It will keep on getting compressed only up to a certain limit. Now, if you are providing excess of negative charge, if you are providing excess of negative charge, now on this particle, now only negative charge will start coming, and it will again destabilize the particle. So due to so much of negative charge, now again the EDL or the electronic double layer size will be increasing, because now many negative charges are coming and destabilizing the particle. So are you getting my point about the second statement? Is it okay?
Yes, sir.
Okay.
Yes, sir.
Yeah. So that's what happens when we are adding too much of coagulant. So if we are adding coagulant only up to a certain limit, it will try to neutralize whatever charge is there over the molecule. Okay, but only up to a certain limit. If you are providing excess of coagulant, it will again destabilize the particle, and the other charge will now start increasing over the particle. Okay, due to excessive dosages. Now next point is ionic strength increases with charge of a coagulant. So this is actually very generic, like, because the more the ionic strength, the more higher charge it will provide. Okay, no, rather the higher the charge, the more ionic strength it provides to any molecule. So that is direct relationship, so that is true. Okay, so this higher charge like majorly contributes more significantly to the overall ionic concentration in the solution. Okay, and this ionic strength is directly related to the sum of the concentration and charge of all the ions are present. So ionic strength is directly related to the concentration and the charge. So more the charge, more the ionic strength will be. Okay, in the solution. So that is directly correlated. So this is the same thing which I have written here. So I have written that initially, as the coagulant dose increases, the ideal thickness will decrease due to charge neutralization and compression of the diffuse layer. This occurs because the added coagulant neutralize the surface charges of the collided particles. Okay, that's what I showed you, reducing the electrostatic repulsion, and it promotes aggregation. However, beyond a certain threshold concentration, further addition of this coagulant leads to charge reversal. So if you are adding more and more, the charge will get reversed and increases the electrostatic repulsion, causing an expansion of the EDL. So that's how the destabilization happens. Okay. So this is about the second question. Now we'll move forward. Particle entrapment in the precipitates during the coagulation is called compression of electronic double layer, adsorption, charge neutralization, or sweep coagulation. So you might have learned about four different kinds of mechanism of coagulation based on uh, whatever ions are present and how much coagulant dosage we are giving. Okay, based on the alkalinity and the coagulant dosage. So based on that, we have four different types of mechanisms. So in what
Is
type
it sweep coagulation?
sweep coagulation? Yes, I think that is the correct answer, because what happens is, so in sweep coagulation, the coagulant hydrolysis happens, okay, and it forms some large precipitates like the metal hydroxides of aluminum hydroxides or ferrous hydroxides. Okay, so these kind of precipitates are formed, which will enmesh these suspended particles and they will settle down. So it kind of sweeps off all the particles or the suspended matter that is present. Okay, so this mechanism is particularly effective when coagulants are added in high dosages, creating a sweep flock that captures colloidal and suspended particles, enhancing their removal from the water. Okay, it will sweep off all the suspended particles. So this happens at a little higher concentration. Okay, so first at lower concentrations, the compression will happen, then charge neutralization will happen, then some sweep coagulation will happen as and when we will increase the coagulant dosages. So just keep a note of that. Okay, I hope it is clear to all of you. We'll move forward. Okay. So this is another question. So just what we are discussing now. So we just have to name it. So here there are three zones like X, Y, and Z in this picture. Okay, so you have to identify what is called as zeta potential, what is the diffuse layer, and what is the electrical double layer. So X, Y, and Z are marked. You just have to Name them.
Is it option B, sir?
Option B. So you are saying the X would definitely be the zeta potential because it is the only thing that is showing the potential. Okay, so we have the potential marked below in the uh, y-axis of the graph. So X will show the zeta potential. Then Y is the electrical double layer. Okay, so that is the distance between the charged particle surface to the end of the diffuse layer. Okay, and then the diffuse layer will be over the charges of the charged particles. So we will just see. So B is correct. So we will look what are these called. So I have written it here. So what is zeta potential? Zeta potential is the electrical potential at the boundary between a charged particle and its surrounding liquid. Okay, so always remember it is the potential between the charged particle and the liquid. Okay, always remember charged particle surface and the liquid. It represents the potential difference between the medium and the stationary layer of the fluid attached to the particle, and it determines the stability of the colloidal dispersions. So based on the zeta potential we will be able to tell, like, if higher zeta potential is there, then strong repulsion between the particles will happen, and only after coming up to a certain potential the attraction forces will happen. Okay, so based on the zeta potential, we can see the talk about the stability of the particle. Then what is diffuse layer? Diffuse layer is the region between the electrical double layer where the counter and ions or the opposite charge ions are loosely associated with the particle. Okay, so between the counter ions and the particles, whatever is the layer, we will call it as diffuse layer. And these counter ions form a gradient of decreasing concentration as we move away from the surface. So closer to the surface, more counter ions will be present. And as we go far from the surface, the concentration will definitely will be uh, going down. And then what is the electrical double layer? It is a structure that forms at the interface between the charged surface and the surface and the electrolyte solution. So between the surface of the molecule to the electrolyte, whatever is my layer thickness, that we call as electrical double layer. So the two parts are stern layer and then the diffuse layer. So stern layer is more compact, or which is strongly absorbed to the particle, and then the diffuse layer which we just talked about. Okay, it's near. So near the particle will be the stern layer, over like which will be closely attached to the particle, and near the bulk solution it will be the diffuse layer. So that's how you can remember. Okay, so just again you can look into the picture. Yeah, so you can see that so the total distance y, you can think it as the total distance of diffuse layer plus the stern layer. So Z marks the diffuse layer which is towards the bulk solution, and whatever is left over part will be my stern layer. So that is being marked here. Okay, and the total thickness is called as the electrical double layer. And in the bottom you can see that whatever the potential between the particle and the stern layer, we will call it as the electrical potential. Okay. Now next question. So for a city of 6 lakh population, compute the fire demand in liters per minute using the Kuchling's formula. So I don't have any options for them. So please try to calculate. It's a single line question. So for a city of 6 lakh population, we have to calculate the fire demand. Please let me know. Do you know the formula for this fire for calculation of for calculating the fire demand? Any idea about the formula?
Sir, is the answer 77,942?
Yes, yes, exactly, exactly. So here the correct answer is 77,942. And how do we get it? It's a very simple formula. It's 3,182 root P. But here you have to take care that this P should be the population in thousands. Okay, so for 6 lakh population, the P will be 600. Okay, so we have to just convert the whatever population is given into thousands. So 6 lakhs is equal to 600,000. So that's why, so that is the only minor thing that we have to take care, and then the answer will be directly in liters per minute. So it's an empirical formula. We cannot justify it with the units. So directly whatever we will be getting will be in liters per minute. It's an empirical formula. Always remember. Don't try to manage the uh, units in this. Okay. Next question. Right. So now we will see a problem regarding the population forecasting methods. So we have to forecast the population for the year 2041 based on the data that is being given here. So through all the methods, like first we'll do arithmetic increase, then geometric increase, and then incremental increase method. Okay, so you please try this. So first we will see for arithmetic increase, then geometric, then incremental. Okay, so please try to calculate with the help of this data. I'll just wait for some time and then I will try. I will go on solving this. So with the same data, we will do all kinds of population forecasting. I'll just wait for 2 minutes or a minute, then we will discuss. Okay, you keep on solving. I will just in the I will also solve side by side, and so that you can match the answer. Okay, so we have the year and the population. So we have 1961, 71, 81, 91, and 2001. And the populations are 6848, 13308, 36707, 58242, and 82149. Okay, so first for arithmetic increase method, we will see what is the change in the population. So that is very important. What is the change in population? So we will subtract this like 13,308 minus 6848. So like that we will keep on subtracting the like the from one decade to the other decade. Okay. So like that we will get the changes as 6460, 23439, and then 21495, and then 23905. Okay. And if we calculate what is the total, so total will be around 75301 for these changes. So just add it up, whatever is the uh, total, we will just find out, and then we will calculate the average. So this by 4, we will get it as 18,825. Okay. So this is what we will get if we find out the total and the average. So as per the arithmetic increase method, so population at 2041. 2041 will be the population at 2001 plus n into the average increase. So n here denotes the number of decades from the given date. So population at 2001 is 82,149. Now n would be nothing but 2041 minus 2001 by, so totally by 10. Okay. So we are finding out in decades. So it will be 10 into the average increase, that is 18,825. So this one, 18,825. Okay, so if we solve it, we will get the answer as 157,449. So it's pretty direct. We just have to find the average change over the years. Over the decades, what is the average change? Okay, so that's how we will calculate for the arithmetic increase method. Now, for the geometric increase method, we have to find the percentage change. So how much percentage it is changing? Okay, so for the first year, it will be 0.943. Then next it will be 1.761. Then it will be 0.585. Then it will be 0.410. Okay, so instead of just only subtracting, we have to find out just the percentage change. And then we will calculate the geometric mean. Geometric mean, which will be nothing but uh, nth root of, like, whatever the percentage changes are there, we will simply multiply it and to the power of 1 by n. So n will be the number of decades. So here n will be 4. So 1 by 4. So 0.9 into 1.7 into 0.5 into 0.4 to the power 1 by 4. So like that you have to do. So if you do that, you will get the average geometric mean as 0.795. Okay, so this is our geometric mean. So if we now do the geometric increase method, so for population of 2041, it will be nothing but 82149. So whatever population is given for the last decade into, it will be 1 plus whatever the geometric mean you got, 0.795 to the power the number of decades from where it is given. So again, it will be 4, because you have to find out for 2041. So from 2001, it is 4 decades. So it will be 4. So to the power of 4. So if you do that, you will get answer as 852,331. So you can see the drastic variation between the two population forecasting methods. This is very high, whereas this has just increased a little bit. Okay, whereas this is like very higher than the other increase methods. Okay, and the last one, the incremental increase. So in the incremental increase, again we just have to find out the incremental change. So whatever the change, now we will just subtract like this. Okay, from 23,439 minus 6460, then we will subtract like this. So this subtraction can be positive or negative based on the change. Okay, so for the first change, the incremental change will be 16979. Then it is decreasing, it is minus 1944. Then again it is increasing, that is 2412. So here also, first we will calculate the total. It will be 17447, and then the average. So by 3, it will be 5816. Okay, so this is my incremental average increase. So as per this, as per the incremental increase method, so population at 2041. First, same as the arithmetic increase method. So 8214 plus number of decades 4 into the average increase. So first this average increase 18,825. Okay, 825. Now we have to add incremental change also. So it will be plus n into n plus 1 by 2 into whatever the incremental average incremental increase. Average incremental increase. So this will be nothing but 157449 plus this whole term will be 4 into 4 plus 1 by 2 into the average incremental increase 5816. Okay, so this will be, so this value you can see is in between, 852331 and larger than 157,449. So this is in between the two. So that's how the, yeah. So that's how the forecasting methods are. So this is arithmetic increase, this is incremental increase, and this is geometric increase. Okay. So I hope this is very clear, very direct. So I don't think much discussion is required.
Sir, I have a doubt.
Yes.
So, which method to adopt, sir? Because there is drastic variation in the forecasted
Yeah,
population.
so this population forecasting, what we do whenever, whenever you are trying to do a population forecasting for a particular for a particular city, we have to see the demographics of that city. Okay, if it's a new city where more and more people are going to come and settle, because suppose IT sector is going to be there, or some industries are coming there, so you expect that more and more people are going to be there in the city in a longer in some 10 or 15 years. So in those kind of situations we will go for geometrical increase. Whereas suppose a city that is already stabilized, okay, the population is slowly increasing, okay, not much industrialization or tourism or anything, not much is happening in that city, and for that you want to design a wastewater treatment plant or water treatment system. So in those kind of cities, you know that the population is not going to change over the period of time. So for that we can have something like an arithmetic increase method. Okay, but then again, if you are not sure whether it will be too fast or it will be like it will be growing too much or it will be very low, then we can subside for something in between, that is the incremental increase method. So based on the dynamics of the city or the area, you have to adopt the methods. And nowadays these are very crude methods. Okay, we will not mostly follow these methods. We will follow something at that S curve method. Okay, that is called the logistic curve method. Either we will follow the logistic curve method, or we will follow some kind of graphical methods where we will see like sector wise or area wise what is the population increase. okay, over a period of time. And then with other aspects, we will try to forecast the methods. So these are very crude way of finding the population forecast. Okay.
Okay, sir.
Yeah. Because why population forecasting is very much essential, because now when we are going to design any water treatment or wastewater treatment plant, we will design it for at least 30 years. Okay, the design period will be at least like mostly for 30 years. Now if you forecast the population too much, okay, then your units will be very larger, so the economics will be too high and you will be spending a lot. Whereas what people generally do now is we go for something called as modular units. Modular, so what do you mean by modular units is, modular units is like, suppose we have a wastewater treatment plant where there is some primary treatment, then secondary treatment, then tertiary treatment. So what we'll say, for the first 10 years we will just make one unit of all these things. Okay, based on the capacity we will just one unit. Then as the population is increasing, we will make more units. Okay, parallelly we will make more units. So in that way we are able to manage the economics. Okay, and we are able to design it better. Whereas if you are like, suppose you are forecasting for 50 years and you are making only in the first year itself a very large unit, then that might not be working very well, because the wastewater flows or whatever concentration that is coming up in the system will not be enough to manage it properly, and a lot of money will be spent on the construction as well as in the construction as well as in the O&M. Okay, so it's always better to have modular units so that you can make the units as and when your population is growing. Okay, so this is another method you can choose.
Yes.
Okay. Yeah. Okay, so the same thing I have discussed here. So everything is there in the slide. You can just go through it whenever you want. So all the increase methods are there. Okay. Now next question. So it says that a water sample is analyzed for coliform organisms by the multiple tube fermentation method. The result of the confirmed test are as follows. So we have three kinds of sample size: zero point 0.1, no, 0.01, 0.001, and 0.0001. And we have given how many positive tubes are there and how many negative tubes are there. So by positive tube, we mean that whenever we are doing this multiple tube fermentation test, if there is a gas release in any of the tube, we will say that microorganisms are present in that. So we will count it as a positive tube. Okay, so out of 5 in the first sample size, we are getting all the 5 as positive tubes, whereas there are no negative tubes. Okay, so like that, the data is given. Now, the most probable number, or the MPN, of these coliform organisms for the above results is to be obtained from the NPN index. So since it's a probabilistic technique, we have already calculated, like, if this is the combination of my positive tubes, what will be my MPN index per 100 ml. Okay, so
110.
110. Okay, just let me finish off the question, because yeah, this is the major mistake that we do. Now this MPN index table is made for a dilution of 10 ml, 1 ml, and zero point 0.1 ml. Okay, whereas our sample size is having 0.01, 0.001, and 0.0001 ml. Okay, so then we have to multiply with some factor and then come to the conclusion. So this is the major mistake that we generally do while calculating the NPN index. So now think about it. So you have the combination of positive tubes. Okay, you know the MPN index as per the dilution of 10, 1, and 0.1 ml. Whereas in the question it is given as some other dilution. So what will be your MPN now? So if you know the test like in and out, like how to do the dilution, how many test tubes are there, what is a positive tube, what is a negative tube, then you will be able to crack it. Just think the dilution. What is the factor that is changed in the dilution level? So there is a complete MPN table that has been formed for various combinations. Here in the question we have given only 4 combinations. Okay, just to make it like in a shorter form. Whereas for all the kinds of sites like 000, 001, 2, 010, all combinations, the MPN index is given, and it is calculated based on some probabilistic technique. Any idea? Like what you told earlier, the answer that is correct to that particular dilution. Okay, you know that the positive tubes you are getting 531. So the combination of positive tube is 531. You have to now look into the MPN index for that. So that is 110. That is absolutely right. Now we have to.
So we might have to use that formula for calculation, sir. Number of positives
No, no,
divided.
no, no, no. Don't have to go into that formula. So now you know the NPN index for the dilution of 10 1 0.1, right? See, so for 10 1 0.1, you know the MPN index. But what you are given? You are given instead of 10, you are given 0.01, right? And then 0.001, then 0.0001. So what is the factor difference here? By how much factor you are diluting? So this is what the table is made of. So this is the table dilution. But in actual you have done this. So how many times more you have diluted? Any idea?
1,000 times.
1,000 times, right? So it will be like 10 by 0.01. It is 1,000. Again 1 by 0.001. It is again 1,000. So all are 1,000 time dilutions. Okay. So whatever MPN index you are getting, okay, MPN per 100 ml, whatever you are getting, the value, you just have to multiply with 1,000. So that will be, so you got it as 110 into 1,000. So that will be 100,000. So this will be your answer. So this is the MPN per 100 ml, right? Is it clear? So
Yes, sir.
just whenever you are reading out the MPN index, always, so why these dilutions are coming? So just I will see, this is the answer. So first find the combination of positive tubes. For others, I am also saying again. So first find the combination. So we found that it is 531. Then see for 531 what is the NPN. So that is 110 given in the table. But now the sample size is for 0.01 and further. So what is the factor that has to be multiplied? That will be 10 by 0.01. So that is 1,000. So 110 into 1,000, we will get 1,10,000. So if you say why this dilution is coming is, in NPN test, we will have 3 sets of data. Okay, 3 sets of test tubes. So suppose I am just showing you 5 test tubes. So what we will do, we will fill this test tube with some media for the bacteria to grow, some kind of nutrient media. Okay, just not think about it. What some nutrient media is there. Now we will add some samples. Suppose you have collected in a beaker a river sample or a wastewater sample, and you want to know what is the number of organisms that is present in the sample. So in the first, for the first set of test tubes, suppose I am taking 1 ml from here and putting it directly 1 ml, 1 ml, 1 ml, 1 ml. So all are 1 ml. Okay. In the next set of data, I will do, I will dilute it 10 times and I will put zero point 0.1 ml. So in all this, I will put zero point 0.1 ml. And for the next set of data, I will put 0.0001 ml. So again diluting it by 10 times. So in this way, I am having three sets of data. Okay, and after that, I will put a inverted tube like this. There are small inverted tubes which I will put inside it, and I will put it into incubation for some 1 day or 2 day like that at a particular temperature. If you are measuring total coliform, it will be 35. It is fecal coliform, then it will be 45 like that. So what will happen if bacteria is there? It will use up in the sample. If suppose in the sample some bacteria is there, it will use this neutron media and it will do some reactions and some gas will be evolved. So if gases are evolved, it will be blocked in this small test tubes. So if we are able to see a gas bubble inside this small test tube, okay, then we will say it is a positive tube. Suppose C are there, so we will say 3 out of 5. So 3 is the positive. Here suppose only 2 are there, so here 2 out of 5. Here suppose only 1 is there, then it is 1 out of 5. So what will be my combination? My combination will be 3, 2, 1. So for that I will search the MPN table. Okay, I will search the MPN table. Now whatever, suppose whatever my X is the answer. So that is for my particular dilution, that is 1 ml, 0.1 ml and 0.01 ml. But now the table is for 10 ml. Okay, or 1 0.1. So how much time dilution? I have diluted 10 times. So whatever X I am getting, I will multiply with 10. So 10x will be my answer, right? So that's how you have to calculate. I hope this is clear to all of you.
Sir, I have a doubt regarding
Yeah,
this MPN test.
yeah, tell me.
Sir, when we are getting these number of positive tubes in the first stage of this, the presumptive test,
Yeah, yeah.
then what is the need of this confirmatory and completed test?
Yeah, so actually sometimes it can be a false positive also. So that's why we do it for three stages. Okay. So that's,
Then how do we conclude the number of positive tubes and negative tubes out of the three tests, or the only for the presumptive test?
no, I think we have to go till the end. We have to go for all these tests, and after only the confirmatory test we will conclude it. So that's how we should do.
That means, like, as you have written, in the first set of five tubes, three tubes are positive,
Yeah.
and these three positive tubes are subject to the confirmatory test and the completed test.
Yes, yes.
Only when they give positive results,
Yeah.
then the positive tubes are counted out of that.
Yeah, yeah, yeah.
So it can be less than 3 out of 5 also.
Yeah, that can also happen. Like suppose first day it is not happen, but we also have to see what is the difference. If there is a too much of difference, then the first day and the third day, then I think there is some problem with the dilution or something has escaped. Okay, some error, manual error is there, then we have to repeat it. Otherwise, at the if there is not much difference, suppose in the first day you are getting all five as positive, and by the third day or the confirmatory test you are getting none of them. Okay, it is becoming zero. Then there is problem with your test, some problem with your test or your conditions. So that then you have to repeat it. But if there is a little bit change only, like out of four, three are still there, then you can proceed with it, and you can just take three as your final positive tubes.
But in any case, I have to complete all the three steps.
Yes, yes, that's how you should do,
Okay, sir.
because we are following that method only in most of our labs. We will do till the confirmatory test. So it depends, like what is the level of risk that you are going to take. Okay, if you just want to know like in a very crude manner, okay, then you can stop with the presumptive or the next level. But if you just want to be very sure about your experiment, or you just want a very accurate data, then it's always advisable to go till the confirmatory test. That's
Fine,
what
sir. Thank
that's what I feel. Okay.
you.
Okay, so now next question. So here also you have to also find the MPN, but using the Thomas equation. So same thing, the sample sizes are given, and number of positive tubes and number of negative tubes are given out of 5. So for this standard multiple fermentation test, you have to calculate the MPN. So I hope you know the formula. Just try it out and tell me the final answer. Is anyone trying, or shall I solve it? Okay, I'll start solving it. So here we have to find out some parameters based on the information that is given. Okay, so first we have to find out the number of positive tubes. So that is nothing but 4 plus 2 plus 1, that is 7. Okay, in the question it was given now. So for each dilution, what is the number of positive tubes? Then the next thing is ml of sample in negative tubes. So what is the sample amount of sample? 127. No, I don't think that is the correct answer. Mm, okay, we'll solve it. Let's see. So ml of sample in negative tubes, it will be, so negative tubes, we have to first count the what are my negative tubes number, then multiply it with the corresponding dilution. Okay, so for the 10 ml, it is only 1. So 10 into 1 plus for uh, 1 ml it is 3, so 1 into 3. Then for 0.1 ml it is 4, so 0.1 into 4, plus for 0.01 it's 5, so 0.01 into 5. So if you add it all up, it will be 13.45. Okay, it will be 13.45. Then next is what is the ml of sample in all tubes. So what is the total ml I am taking? So for 10 ml 5, 1 ml 5. So for all the mls I am taking 5 test tubes. So it will be 10 into 5 plus 1 into 5 plus 0.1 into 5 plus 0.01 into 5. Okay, so it will be around 55.55 ml. So now as per the equation, it says that mpn, uh, so mpn per 100 ml will be equal to nothing but number of positive tubes into 100 divided by under root ml of sample in negative tubes into ml of samples in all tubes. Okay, so this is the equation. So for positive tubes, number of positive is 7. So 7 into 100 divided by under root 13.45 into 55.55. Okay, so if we solve this, we will get something around 25.069, or we can say approximately 26 mpn per 100 ml. So this is the answer. Okay, I think this calculation is correct. You can cross check it. If there is any discrepancy, you can let me know. So that's how you have to do. First, find out the number of positive tubes. Then what is the ml of sample in negative tubes? Then ml of sample in all the tubes. And then apply this formula, you'll get the answer. And one more thing, Jyoti, like where you are discussing about this, like why you have to go for till the confirmatory test is because suppose this presumptive test, sometimes this false positive can come due to a certain kind of bacteria also. Like if I want to find out only the coliform bacteria, this presumptive test can give positive results due to some other kind of bacteria also instead of the coliform bacteria. So that can be another reason, like why we have to go till the confirmatory test to confirm the presence of only coliforms, not any bacteria but coliforms. Are you able to get my point? Hello, am I audible? Okay, I think she is not online now. Okay, anyway, I hope others you have understood my point. So, yeah, the same thing is marked here. Okay, okay, moving forward. So match the typical water quality parameters with the respective categories. So we have chemical, physical, biochemical, and microbiological category. So and the some parameters are given. So please tell me the correct option after matching. D. So chemical parameters. Uh,
Salinity, hardness, and heavy metals.
So that will be my chemical parameters. Okay, then
Yes.
so
Physical taste and odor
odor,
and temperature.
that is true. Then biochemical,
Biochemical BOD and TOC.
POC, and microbiological will be pathogenic.
Microbiological pathogens, VSS, and viral pathogens.
That is absolutely correct. So C will be my correct answer. Okay. So very simple. I think not much discussion is required. Okay. Zeta potential is the electric potential between the shear plane and the particle surface. True or false? Just in one word, you have to tell me. Zeta
True, sir.
potential. Sorry.
True.
True. Are you sure? Just think about it. So the answer is actually false because it is the potential between the shear plane and the bulk solution, not the particle surface, but the bulk solution. Okay, very small difference, but from the plane to the bulk solution, what is the potential difference? We will call it as zeta potential because after overcoming that only, we will be getting the attractive forces. Till then, it will be repulsive forces. Okay, so very subtle variation, but this is false. Next one. Select the correct characteristics of a coagulant required for coagulation. Okay, so we are talking about coagulation here. Non-toxic at working dosage, should be having high charge density, should be having low charge density, insoluble in neutral pH range, soluble in neutral pH range. So what do you think should be the characteristics of a coagulant?
Soluble in neutral pH range.
Okay, what else? Anything else? There can be more than one correct answer.
I think should be having high charge density, sir.
Should be having.
High charge density.
Okay. Anything else? So first point of discussion is whether should it have high charge density or low charge density. Okay, so definitely a coagulant should have a high charge density. Okay, so that is very much clear. And then should it be soluble or insoluble? So what do you think? So if it is soluble, will it be able to precipitate?
It's a insoluble.
It should be definitely insoluble. Okay, if it is soluble in a particular pH range, then it will not precipitate out, right? And if it is not precipitating, the flock forming capability will not be there. Okay, we want the suspended particles to settle it with the coagulant. Okay, so that's why it should be insoluble in the neutral pH range. And mostly if it is not insoluble in the neutral pH range, we will adjust the pH accordingly. We will move into the alkaline region or the acidic region based on our coagulant. So that's why it should be insoluble in the neutral pH. This is for ideal condition, and definitely it should be non-toxic. Okay, if it is toxic, then again it will cause some other kind of issues. So all A, B, and D should be the correct answer for any coagulant, for an ideal coagulant to be used in coagulation.
Excuse me, sir.
Yes.
Please define non-toxic working dosage for clarified.
So non-toxic means, suppose how to say, suppose whatever dosages we are providing in the system, okay, suppose 2 milligram per liter or 20 milligram per liter, it should not give any toxicity characteristics to the water, because that water has to be used, okay, has to be consumed at a different stage. Now if it is making it toxic, suppose some heavy metals are coming out, okay, from the alum, or some other toxicity characteristics are there, okay, then it will, then that has to be also removed, right, at after certain stages. So we don't want that in the initial stage also. So it should be non-toxic. At whatever dosage we are providing it, it should not affect the human body.
You mean to say, suppose I want to know more toxic means?
More toxic means, like, if it is consumed to the human body, some effects will be there.
Okay, sir. Okay.
Okay. So, in whatever dosage you are giving it, it should not affect the human body, or there is no need of another treatment to remove that toxicity, that kind of toxicity. So, that's what I mean. Okay, the next one. About coagulation theory, the net force on the colloids is repulsive at greater distances and becomes attractive only after passing through maximum net repulsive force called energy barrier. The above statement is relevant to which of the following mechanism? Ionic layer compression, interparticle bridging, sweep coagulation, or none of the above. So what mechanism gives this theory that at greater distances repulsive forces will be there, and only after uh, going through a particular potential we will get the attractive forces or the energy barrier. After overcoming the energy barrier, we will get the attractive forces. So what coagulation theory will tell this? I think we have to move a bit faster because still many questions are there. Okay, so please try to answer as quickly as possible. Then we'll be able to finish. A. So that is nothing but ionic layer compression, because uh, what I discussed in the first problem is the same thing. Okay, this diagram which I was focusing on. So a particle with some charges over it. Okay, so first at lower coagulant dosages or whatever, there will be more and more repulsive forces, because the compression is not happening. As slightly we are increasing the coagulant dosages, this charge will start getting neutralizes, and the repulsive forces can be overcome after overcoming the energy barrier, and then the attractive forces will come into the picture. Okay, and I also showed you what are the various layers: stern layer, diffuse layer, okay, and then the bulk solution. So all these things will be happening in the ionic layer compression. So in the detailed answer I have written, at greater distances, the net force between two colloidal particles is repulsive due to electrostatic double layer interaction, or the EDL. This repulsion arises from overlapping electrical double layer surrounding the particles, preventing aggregation. Now, as the particles move closer, the repulsive forces increases, reaching a maximum repulsive energy called the energy barrier. And this barrier prevents two particles to come in contact with each other. Beyond the energy barrier, the particles come even closer and the van der Waals attraction becomes dominant. So this van der Waals attraction is nothing but the attractive forces. And then this attraction overcomes the repulsion, leading to irreversible aggregation or coagulation. So that energy barrier we have to overcome to get into the attractive zone. Next one. Again, a small numerical. It is very generic. So we have been given an information about a community where the present population is 34,000 and after 20 years it is expected to be 52,000. Now present water consumption is 3,700 meter cube per day and the water treatment for the design capacity is 5600 meter cube per day. Now using arithmetic rate of population growth, the number of years from when the plant will reach its design capacity will be. So you have to find out in how many years the design capacity will be reached. So we have a present population and the expected population in 20 years. Okay, and present water consumption is also given and what is the design capacity. So in how many years do you think the design capacity will be reached if there is an arithmetic increase of population growth? So that means per year or per decade, the increase is constant. So we have to assume that the increase is constant per year. Okay, so just make a note of this question. I will solve it. So question number 13. So first we will find out what is the average increase per year because that is very much important for our assumption. So average increase in population per year. Okay, so let it be X bar. So final year it is 52,000. What is the present population is 34,000. In how many years? In 20 years. So average increase is 900 per year. Okay. And what is the design discharge? So present discharge, design discharge is present discharge is 3,700 and it will go up, it can go up to 5,600. So whatever is the remaining design discharge, so it will be 5,600 minus 3,700. So this much discharge can increase. Okay, can increase. So after this, what we will find out what is the present average water consumption per head per day. So per day, one person, how much they are consuming. So presently, the discharge is 3,700 meter cube per day with a population of how much? 34,000. Okay, so what is the water consumption? It will be 0.1088 meter cube per person per day, right? So per person per day, this much they are using. And how much it can increase? It can get increased by 1900. So what will be my increase in each year? So in each year, we are increasing the population by 900 and per person it is 0.1088. So it will be 0.1088 into 900. So this much meter cube per day can increase in 1 year. In 1 year. So what is the total number of years?
900 or 1900, no?
900. We got 900, right?
Okay.
Okay, 900. So number of years to reach the capacity. So we have a leverage of 1900 divided by 97.97. So it will come out approximately as 19.4 years. So we can say by 19 years we will reach the design capacity. So very simple, just simple arithmetic. right? So that's how we have to solve this problem. Actually, outside it has started raining. I think the internet can go anytime. Okay, there can be a power shutdown or Wi-Fi problem may be there. So we will try to finish off as soon as possible. Okay, so we will focus mostly on numericals now. Now next problem, compute the fire demand for 1.5 lakh population by using the America Insurance Association or the National Board of Fire Underwriters formula. Okay, so here you have to find out the fire demand in MLD using by using a particular formula, which is called as the America Insurance Association or the National Board of Fire Underwriters formula. So any idea about this formula? Anyone? So I will just tell you the formula. So the formula for this is equal to Q equal to 4637 under root P into 1 minus 0.01 under root P. So again, here the answer that we will get will be in liters per minute. Always remember these empirical formulas will give the answer in liter per minute. And the population should be in thousands. So for 1.5 lakhs, it will be 150. And the final answer will be, we will be getting in 49385.9 liters per minute. But in the question, it is asked in MLD. So you have to change the unit. So the final answer will be 71.763 MLD. Okay. Very
Sir,
simple.
MLD means millions liter per day or
Million liter per day. Million liter per day. Yes.
yes.
Million
Okay.
liter per day. Okay. Okay. The next problem, I'll quickly go. If the average daily demand of a city is 150,000 meter cube, the maximum daily consumption in meter cube will be. So average daily demand is given. You have to find out the maximum daily consumption. So what is the factor? Any idea?
2,70,000. Option D, sir.
2,70,000. So definitely we just have to multiply with 1.8. So the factor from average daily demand to maximum daily demand will be 1.8. So 2,70,000 meter. Okay. I'm skipping the theory questions for now because we have discussed all types of. So I'm basically concentrating on the numericals. So a certain water needs 12 ppm of alum dosing. The amount of alum needed for 10 mld of water per day is. So how much alum will be required for 10 mld of water? If, if the dosage is 12 ppm. So please tell me the answer. So the answer has to be in kgs.
Option B, 120 kg.
Yes, I think it's right. Because directly it will be 12. So 12 ppm is nothing but 12 milligram per liter. So 12 milligram per liter into 10 mld means 10 into 10 to the power 6 and liters per day. And then this kg we have from milligrams we have to change it kg, right? So it will be 120 kgs per day. So in per day it will be 120 kgs, right? Very simple. Okay. I think this kind of problems we have solved last time. So I will just go to the final question, I think. Just a minute. Yeah. So this is the question. It's a little big question. So just see how to solve this. So 40 mld of water is being treated with 18 milligram per liter of alum in a water treatment plant. So now calculate the yearly alum requirements. So this is the first question. Then second, it says that if the water contains 5 milligram of CaCO3 of alkalinity, calculate the amount of calcium oxide of purity 85% that is required. So again, the first part of the problem remains the same as the previous, as one of the previous problems. So for 40 mld, what will be my alum requirement per year? So here for particular, for 1 year they have asked. And then it is saying the water itself is having an alkalinity of 5 milligram per liter as CaCO3. So what is the extra alkalinity or calcium oxide we have to add to balance the alkalinity? Because for alum we need, it will take up the alkalinity, right? So how much extra we have to add? So this is the question. Okay, I hope you understood it, the part of the question. We'll see how to solve this. Any idea, like 1 gram of alum will react with how much gram of alkalinity? Any idea? Because then only we will be able to solve this problem, right? So what do you think? 1 gram of alum can react with how much gram of alkalinity? Do you know about these ratios, anything? So actually there is a derivation also. Maybe I can take up in the next class. For now we don't have much time. So uh, yeah, so for 1 gram of alum, it will react with 0.45 gram of alkalinity as CaCO3. So alkalinity we already defined is in terms of CaCO3. So 1 gram of alum will react with 0.45 gram of alkalinity as CaCO3. So always remember this. So to solve any kind of problem, this will be required. Okay, we will solve this problem. So what is happening is, in this reactor, some 40 mld of water is coming, and we are putting alum dosage of 18 milligram per liter of alum. Okay, we are putting, and inside this water we already have 5 milligram alkalinity as CaCO3. Okay, so for the first part we have to calculate the quantity of alum required yearly. So quantity of alum required yearly will be nothing but 18 milligram per liter of alum into 40 mld into 10 to the power 6 for million liters to liters into 365 days. Okay, and I am converting everything into tons. So let's suppose I am converting everything into tons. So it will be 10 to the power minus 9. Okay, instead of kg I am converting into tons. So it will be 262.8 tons of alum per year for 365 days. So this much of tons of alum is required. Okay. So now next part. So now next part we want to find out how much CaO has to be provided added additionally into the system. So as I said 1 gram of alum reacts with 0.45 grams of alkalinity as CaCO3. So this is the thumb rule. Okay. So for 18 milligram per liter of alum, that will react with 18 into 0.45, or I can say 8.1 milligram per liter of alkalinity as CaCO3, right? Because 18 milligram per liter alum we are adding, so it will react with 8.1 milligram of alkalinity as CaCO3. So what is the additional alkalinity required? So in the system we already have, so we need 8.1, and in the system already 5 is there. So 8.1 minus 5, so that means 3.1 milligram per liter of alkalinity is required additionally. Now This is required as CaCO3. Okay, but what we are adding? We are adding CaO. So the reaction will be like CaO. It will be hydrolyzed, and we will be getting CaOH twice, and then further it will be carbonated, and we will get it as CaCO3. So if we add 1 mole of CaO, we will get 1 mole of CaOH twice to get 1 mole of CaCO3. So everything is in 1 mole. So I can say 1 mole CaCO3 is induced by 1 mole of CaO if it is of 100%. So let's imagine instead of the 85% purity, I am considering 100% pure CaO. So 1 mole of CaCO3 will be induced by 1 mole of CaO. So what is the weight of 1 mole of CaCO3? It is nothing but 100 grams. Right? It is 100 grams. 100 grams CaCO3 is induced by 1 mole of CaO. 1 mole of CaO is equal to 56 grams. So just the molar weight of CaO of 100%. Now CaCO3, how much I need? I need 3.1 milligram per liter. So for 3.1 milligram per liter, CaCO3 will be induced by 56 by 100 into 3.1. So that is nothing but, so let it be some number. So this is required for 100% purity. That much is required for 100% purity. Now quantity of 85% pure CaO will be equal to this number, whatever number we got now. Okay, this much milligram per liter as CaCO3. Now it is 85% pure, so we will be dividing by 0.85. So more amount will be required than the necessary because purity is lesser, into what is the MLD of water that is coming, that is 40 into 10 to the power 6 liters per day into 365 days, and convert into tons by 10 to the power minus 9. So we will get the final answer as 29.8 tons per year. So that's how you have to solve it. Is there any problem in understanding this question? Just I will go through it once again. So first, we know these parameters are given. 40 mld is the discharge. The alum concentration is also given, and some part of alkalinity is also there. So first, how much alum is required? So that is nothing but the concentration into the discharge into the number of days, and then convert it to tons. Then to find out the alkalinity, 1 gram of alum always reacts with 0.45 grams of alkalinity as CaCO3. So for my 18 milligram per liter, it will require 8.1 milligram per liter as alkalinity, okay, as CaCO3. So 5 is already there, so we need extra 3.1. Now this alkalinity is coming is in terms of CaCO3, but what we are putting is CaO. So 1 mole of CaO will react to give 1 mole of calcium hydroxide to give 1 mole of CaCO3. Okay, so we can say 1 mole of CaCO3 is induced by 1 mole of CaO if this is 100%. So for 100 grams, we will need 56 grams. For 3.1 milligram per liter, we will need 56 by 100 into 3.1. Now for 85% pure, it will be just divided by 0.85 into the discharge into the number of days. So that will be in, suppose, kgs per year or tons per year, whatever you want. Is there any problem? Okay. Okay, so that's all for discussion for today. I think I have to stop it because I am thinking that the internet might go now. So I think I have finished all the numericals that was required for today. Some maybe some theoretical questions are there, but the similar kind of questions we have already discussed in detail regarding the EDL and coagulation, flocculation, everything. So you can go through the PPT once if you want. Hardly some 3-4 questions are there, very generic, and all the numericals I have discussed for now. So still, if you have some doubts, you can ask me now, or you can reach out to me in my email address. So we'll meet again on 18th March, Tuesday, 7 to 9 p.m. Okay. If you don't have any concerns, you can leave the session. You want to ask anything, Jyoti? I think you are muted. Thank you, Mohan.
Thank you, sir.
Okay, thank you.
Welcome, sir. Bye, sir.
Bye bye.
Akash sir, one small query.
Yeah.
Sir, this fire demand, we have to memorize all the empirical formulae.
I think these two are enough for Quichling's formula and this underwriter's formula. That is enough for you. So that's why I had both of them. There are actually several formulas, but these are majorly used. So I think for exam point of view, this is enough.
Okay.
Okay.
The Freeman and the one used in India Ministry of Urban Development.
See, there are so many things are there, but you for if you are just concentrating for this exam purpose, I think these 2 3 are enough for you. Okay, mostly the skitchlings will be asked, but I don't know. Maybe if this time they ask something else, it's up to the discretion of the examiner, to be honest. But these two formulas are majorly used, so that's why I've kept it in the. Uh,
But in India, do we actually consider this fire demand, sir?
yeah, in the design, it is being considered. Definitely, fire demand is being considered, but we also have a hell lot of other factor of safeties. So ultimately, everything will be taken into consideration, and then it will be designed. Fire
But
demand is a very
do we have the fire hydrants installed in the metro cities and the towns in India?
it's not only about the fire hydrants. Maybe like what to say. I'm not very much sure about the planning and design. As far as I know, it is there in the water supply system, but how is it being executed? I'm not sure, to be honest.
Because somewhere I read India being mostly of the concrete structures,
Okay,
so we don't that frequently encounter the fire hazards.
okay, you are thinking in that aspect, but no, I think it is there in the design. It's not about only the concrete structures, but what about the other areas? Okay, so because in a short amount of time, the discharge required is very high. So if you are not incorporating it, then if in case any fire hazard happens, then we will be short of water.
But most of the times we carry the water through the fire
Fire
engine,
trucks, you are saying.
fire trucks,
Uh, yeah,
because
so
none of the incidences I've seen they connecting it to the fire hydrants.
okay,
Because I myself am a assistant professor in a college, and
okay,
quite frequently my students pose this question to me, "Ma'am, there are no fire hydrants in our city." Then I just googled it out, and I came to know that in India, maybe only in Mumbai and some very well planned cities, we do have the fire hydrants. And I thought only in those cities they might consider this fire demand, and none of the other cities.
okay. No, I am not sure, but mostly like whenever like we are designing for anything like any consultancy projects and all, we will try to keep this. I'm not sure how is it executed, uh, but we will take this into the consideration.
Then mostly adopting what formulas are out of them?
Mm, basically, I am the like we like I personally have not done, but in consultancy I have seen some where this underwriter's formula being used.
Okay, sir.
Okay.
Thank you, sir.
Yeah.